We have carbon monoxide at standard temperature and pressure enters a well-insulated reactor and reacts with 100% theoretical air entering at the standard temperature and pressure. An equilibrium mixture of CO2, CO, O2, and N2 exits. So this is the inert. N2 is inert. It's just going for the ride. CO is because of the dissociation. And it says now, for steady state operation and negligible effects of kinetic potential energy, determine the composition and the temperature of the exiting mixture. So this temperature that you're going to calculate is the not adiabatic flame temperature, it's our equilibrium temperature, right? It's our equilibrium flame temperature. And the composition. So what we're asked to solve for is temperature, equilibrium flame. If you want a different subscript on that, that's fine. And then what are we asked to solve for here? Well, we could put in Y of CO2 and Y of CO and Y of O2 and Y of N2. Wouldn't that be a good description of our composition of our mixture? It sure would. So let's go ahead and start this problem. Go back to just a reaction equation for 100% theoretical air in complete combustion. Here it is. CO2. No, not CO2. What are our fuel is carbon monoxide, right? CO plus O2 plus 3.76 N2 goes to, so I'm going to show one arrow, complete combustion, and it's going to go to CO2. Is the carbon now balanced? Yes, it is. How about the oxygen? What is the number there? And I'm going to stop and pause and see how many people can correctly calculate the coefficient in front of the O2. This is one of those cases where O is with the fuel. I'm going to do that in a minute. But right now we can balance the oxygen. Oh, there's no hydrogen. So there's no water in this exhaust in the products. You're right, there's no hydrogen. 0.5, isn't it? Okay, somebody says 0.5. Okay, or somebody says, well, the two choices are you either put 0.5 or 1, and both cannot be correct. So one is correct and one is incorrect. But one incorrect would typically be given on an exam because they failed to look at what? The fuel. And they failed to see that there's some oxygen coming in with that fuel. Very few times there's oxygen coming in with the fuel, but sometimes, as in this case, there is some oxygen coming in with the fuel. So in this case, what is the coefficient needed? 1/2. Now the oxygens are balanced, true? And now we can finish it out with the 1/2 3.76 N2, and yes, there's no water vapor in this product. So this is a very simple case, pure carbon monoxide being combusted. So we can handle it. These problems get very difficult with all the tedious math and bookkeeping to take into account. I'm going to rewrite this. CO plus 0.5 O2 plus 1.88 N2 goes to CO2 plus 1.88 N2. I just like to put the 1.88. Okay, now this is if you have the 100% theoretical air and it goes to complete combustion. But what we're going to have is we're going to have dissociation of the products. That's like incomplete combustion because the dissociation that's going to occur is for this component, true, and that component's going to dissociate to CO2, goes to dissociate with CO and 1/2 O2, true? Is that balanced? Is that our reaction equation that's in the table? The dissociation reaction equation that's in the table that we can get a K for? An equilibrium constant for? right? So one way to model this is to say that really not all the CO was combusted. And that may help us link together what we studied before in this one. So what I'll do is I'll say, if you had 100% combustion, then you would get, yes, all of the CO2 and 1.88 N2. But if you didn't, let's say that I had Z is defined as, or introduced to be, the fraction not combusted. Not combusted. And so 1 minus Z is the fraction that is combusted. Does that make sense? So I have this parameter Z. All right. So I'm going to come in with CO plus 0.502 plus 1.88 N2. And it's going to go completely to the fraction not combusted, Z, times CO plus 1/2 O2, or 0.502, plus 1 minus Z, the fraction that is combusted. And when it is combusted, it gets CO2, plus the 1.88 N2, and the 1.88 N2 just goes for the ride. That's why I didn't put a Z in front of it and a 1 minus Z in front of it. It just goes for the ride. Now, does this equation, is this balanced? Is it balanced in C's? Is it balanced in O's? It's definitely balanced in N's. Well, I mean, we can count it up. You'll have Z, let's do the carbons. Z plus 1 minus Z, guess what? That's 1. Over here it's 1. So it's balanced. Okay, let's now do the oxygen. It's Z plus Z times 1/2 times 2. So it's plus Z, right? Plus 1 minus Z times 2. Did I do does it look good for the, okay, and guess what this is now equal to? Just 2? You do the math, 2. We come over to this side. We have 1 plus 1/2, 2. Hey, is that 2? So it checks. It's 2 and 2. It's balanced on the O's. Okay, and the nitrogens are balanced. So just, there it is. Okay, now that we've written that, now what we want to do is we want to think of applying our chemical equilibrium, our, it's like a CHEM, chemical equilibrium equation. And then we're going to do our thermal equilibrium equation, our energy balance. So what's our chemical equilibrium equation? If we had our equilibrium constant K for that reaction, it's a function of temperature. A lot of times they'll say, hey, don't forget, it's a function of temperature, so they'll write it like that. First time you see that, you may be fooled. You may say, oh, K times T. But it's not. They're just emphasizing it's a function of temperature is equal to, in this problem right here, this is our dissociation equilibrium reaction of interest. So it'll be the amount of carbon monoxide raised to the 1 power, the amount of oxygen raised to the 1/2 power, divided by the amount of carbon dioxide, CO2, raised to the 1 power, times the pressure divided by 1 atm, divided by the total N. The total N is the number of moles of carbon monoxide, the number of moles of oxygen, the number of moles of carbon dioxide, and the number of moles of nitrogen, true? All of that raised to the power 1 for the coefficient in front of the CO2, plus 1/2 for the coefficient in front of the O2, minus 1. Okay. Did all this make sense? Where might you see a student make an error? Plenty of places, true? But sometimes it's confusing of, sometimes, this NO2 to the 1/2, Okay, well, I think this is fine. Let me go ahead and write out K is equal to the number of moles of CO2, CO, carbon monoxide. What is that in looking at this side of the equation right here? See? What is it in terms of Z? Is that equal to Z to the 1? How about the number of moles of O2? Is it Z over 2? And then I have the square root of that? Okay. Let me kind of look at this. Looking right in here, the number of moles of CO is Z. Looking right in there, the number of moles of O2 is equal to 1/2 Z. How about the number of moles of CO2? Looking right in here, it's 1 minus Z, and the number of moles of N2 is 1.88. True? We don't know Z. We're going to solve for Z. But this is, Z has to satisfy this chemical equilibrium equation. So it's 1 minus Z all to the 1 power. Okay, our pressure is 1 ATM, isn't it? So if they said it was 5 ATM, coming out at 5 ATM, that would have an effect. The pressure would have an effect, but it's just 1 ATM. So it's 1 over the number of moles of CO, Z, plus 1/2 Z plus 1 minus Z plus 1.88. All of that to the 1/2 or square root. We can simplify this, can't we? We can put this Z over 2 to the 1/2, 1 minus Z. What is this here? That cancels. So it's going to be Z over 2 plus 2.88 to the 1/2. True? Is it 2.88? Do you see that? Thumbs up if you agree. A couple more. Don't sleep on me. Does it look good or not? That's our equilibrium equation. Guess what? We don't know the equilibrium flame temperature. I don't know what K is. And if I don't know what K is, I can't get Z. Normally, somebody gives us K so far, or gives us the temperature so we can get K. But this is a challenging problem because we have a chemical balance equation, that's right here, and we have to write our energy balance equation. Let's go and write our energy balance equation. So now the energy balance equation for equilibrium, right? What does that look like? How about Q dot divided by N dot F? I know it's adiabatic. We'll strike that, make that equal to 0. Plus sum of all the reactants, N times H bars, minus the sum of NH bars of all the products equal to 0. It's adiabatic. So what we end up with is the sum of all the coefficients times this enthalpy for the products minus the reactants equal to 0. So let me write it like this. Sum over all the products of NH bar minus the sum over all the reactants NH bar equal to 0. True? So let's write it out. Okay? Thinking about this. Okay. We go back to our equation right here. Isn't this our reaction equation? True? And it's going to make now a long energy balance, but for the products. So we're going to have Z times enthalpy formation plus the enthalpy at the equilibrium flame temperature minus the enthalpy at the reference temperature. All of those are for the first component, carbon monoxide, plus Z over 2 times the enthalpy formation. I know it's 0 for oxygen, but I'm going to write it, plus the enthalpy at the equilibrium flame temperature minus the enthalpy at the reference temperature for oxygen. I need to scoot down just a little bit. Plus 1 minus Z times the enthalpy formation for the carbon dioxide plus the enthalpy at the equilibrium flame temperature minus enthalpy at the reference temperature, CO2, plus 1.88 times enthalpy formation plus enthalpy at the equilibrium flame minus enthalpy at the reference. All of this for the N2. Now we have minus the sum over all the reactants. So we have 1 times enthalpy formation plus, now look at, what is the enthalpy of the temperature coming in minus the enthalpy of the reference temperature for all of these carbon monoxide. But isn't that 0 just because the inlet temperature is the reference temperature, 298? Okay. Minus 0.5 or 1/2 times the enthalpy formation plus delta H bar for the oxygen minus 1.88 enthalpy formation plus delta H bar for the N2. Okay, so coming in, they had no elevated temperature. And then also we know that O2 and N2 have a 0 enthalpy of formation. So all those values that I struck are 0. True? I didn't say it was easy, did I? Not at all. But this equation is 0 is equal to everything, right? I'm just going to erase this, a little confusing. 0 is equal to all of that. And so for the energy balance, you need to know the Z. The Z was the fraction not combusted. And you need to know the temperature of the exit. That's the equilibrium flame temperature. So you have two unknowns in the energy balance. And if you go back to the chemical balance, it just has Z in it. True? Doesn't it have just Z in it? Okay. What I'm going to attempt to do in the next few minutes is to say how you would do this or show you how to do this in Excel. And I think if you follow along with Excel, you can do it by hand as well. But let me try and turn this around and get set up and go to Excel and try and solve this. All right, you didn't see the previous sheet that had the solution in Excel, right? You don't want to see that. You want to see how you build it. Yeah. Just looking at somebody else's built, it's like, So anyway, what I would do is I would pick right up the top and I would say the temperature equilibrium. And I would say, this is something I don't know, and I'm going to iterate on it, and I'm going to start with like 1500 Kelvin. So this is this equilibrium temperature. Maybe I put my units for it, but this I know I'm going to have to iterate. It's not a simple algebraic equation where you just say, get everything on one side and then divide over, and then you have x is equal to some ratio. No, it's not. It's hard math. And then z. Didn't we say that we didn't know what that was? We could start with a guess, 0.1. Maybe it's 0.05. These are going to be iterated or guessed or changed to find the solution. Sometimes I like to color code them to help me say, oh yeah, that one is color coded to be something that I know I need to iterate a value. Okay, now the other thing is before I get to getting the chemical equilibrium equation, I better get K, which is a function of temperature. What's temperature is it a function of? It's a function of the equilibrium temperature. which if I guess to be 1500, I'm going to have to jump into the table, get it at 1500. If I guess it to be 1600, I'm going to have to go into the table and get it at 1600, isn't it? Real pain. But let me show you how to do that in Excel. You get your data somehow already copied from the table. All right? You say, that looks pretty brain dead to copy it. I know, I did it. I'm brain dead. You then paste it somewhere on your sheet. So what I want to do is when this value is 1600, I want to bring back that value. See that? When this value is 2100, right? I want Excel to put in this cell that value right there. All right? Now, there's probably a couple ways to do it, but when Excel is 2000 here, what value do I want right there? I want it to interpolate. I want it to interpolate, right? After some research, I'm going to show you two functions, percent rank. And you can look up more about these in .inc, okay? And whenever you find it, you can then scroll down or up and get the right one, hit tab, and it finishes it out. And it says, give me an array. Then give me the x value into the array. Well, I'm going to be looking at coming in with temperature, true? So I give it the temperature array, like that. Then I need to tell me what x value is coming in. I want it, come on now, work. 2000, whoops. What happened here? That sure did mess up. Let me put this over here. Okay, I need to hit a comma. Now I'm ready to put in the 2000. And this significance is how many significant digits do you want? I'm going to show you, I'm going to pick 3 and then we'll change it. I'm not really trying to teach you Excel, but now to get the y value, I need to get the, instead of the percent rank, I need to get percentile. Percentile, like that. Hit the tab. And it's looking for the array first, so I give it the array first. Hit the comma. Come back and look. The second part is, you can see the little help down here, is the kth value, but guess what? We're giving it the percentile rank. I just need to close this parentheses. So does 500, does it return back this value? Well, it's close, but it's not perfect. The reason it's not perfect is I needed more significant digits. I needed more digits there. If I put 7 and hit return, it gives me the value. Okay? This took me a long time to figure out in Excel. If you ever do anything like this, anyway, there you go. So now if I come in with a value of 400, it will actually handle the interpolation. If I come in with a value of 2000, it's not in the table, but it handles the interpolation. So now I'm able to get k as a function of t, where that t is at the top of my spreadsheet. So, okay. Now, what about my equilibrium equation now that I have k of t? How about just equilibrium chemical, something like that? Okay. That is, the equation is equal to 10 to the power k. Is that right? Yeah, no, I need to get k, so I need to get, what I just got was the log base 10 of k. I need to clean that up. Let me hit this, come back here, log, or just do this. Well, no, I like log 10 of k. How's that for a cell? Okay, so now I have 10, so that's what k is. And now I have to type in the other side of the equation. So I subtract, and what was my equation? Was it z times square root of z divided by 2 divided by 1 minus z? So far, so good? Times, in parentheses, 1 over what did we have in the denominator? We had 2.88 plus z divided by 2, close, close. And I could raise it to the half power, or I could just square root the whole thing. That equation looks good. Now it's not equal to 0. This equilibrium equation needs to be 0. It's only a function of z. Do you see that? So what I do is I come over and I say data, what if, goal seek, and I say set cell C4 equal to 0 by changing cell C2. And there's close enough, okay? Let's say that I don't like this value right here is small, but I want it to be, really want to drive it to 0, okay? So sometimes I'll boost its magnitude, and then I'll do it again and see if this value changes. Kind of remember this value right here. See if this value changes. What if goal seek, drive it to 0 on that value? It did change a little bit. It's fighting with that third digit out there, that third significant digit. Cell doesn't understand like 10 to the minus 6 may not be small. It says, oh man, that's small. But what happens if I change this value to 2500? Now, if I'm going to resolve at 2500, do you think z is going to go up or down? Z is the extent of the dissociation, right? So it's going to go up. It's going to go up. So here I say, what if? See if it does go up. Goal seek. Change it to value 0. Find the new z at that higher temperature. And it went up. See that? 17% didn't burn. That's probably too high. Probably too high. So as a good guess, I'm going to boost this back down to 2000. And I'm going to resolve what if analysis, goal seek, set to 0, and set that to about, okay, that's 2%. That seems too small. But anyway, let's continue on because I've got a lot to cover. We've already done the energy balance before, have we not? What did we do? I put everything on the ends, and then I said, well, of the ends, what do I have? I have CO coming in, I have O2 coming in, I have N2 coming in. I have to get the number of moles of each of them. There was 1 here, there was 0.5 here, 1.88 here, true. I'm going to have to get the enthalpy of formation. I'm going to do N times enthalpy formation. Okay, I'm going to copy from another sheet because I'm running out of time. All of this, oops, I only want to get this far. Copy, come over. You didn't see that. So what I did was I did the sum over all of the N's, over all the reactants of N times the HF plus HI minus HREF, true? And then I did the sum over all of the outs, or all the products, so the same N times HF plus H at the going out. This exit temperature, though, is the equilibrium temperature that I pick. So notice that I color-coded this blue. If this changes to 2100, these all change. These enthalpies all here change. Look at a couple of them. This is enthalpy of CO2 as a function of temperature using that 2100. Okay, so then for an energy balance, it's the sum, this minus that, true? Or products minus reactants. But you want to drive that to 0. So what we could do is we could come up here to what if, goal seek, and set that cell equal to 0 by changing the temperature. True? And there you go. So it would say, oh, it's 2600. But I know at 2600 there's not more dissociation. So Z is not there. So what you have to do is you have to kind of iterate, and without doing a lot of things, what you can do is have one error and try to minimize it, changing 2. But this is very nonlinear. Sometimes the root binding doesn't work. But if I take the energy balance, and I square it, and I add to it the equation or equilibrium chemistry squared. That will give me this quantity squared plus this quantity squared. I'll have one error, and I want to minimize it, and this one I want to change both of these. It ain't going to work, but I'm going to show you not working. How's that? I would go to Solver. It's under Data. Solver says go ahead and minimize cell C18 by changing, and here you can select more than one variable with Solver. GoldSeek you couldn't. So solve for both of those, and you know what? It did work. I'm amazed. But if you're not close to the real solution with your guess, a lot of times it won't work. It's nonlinear. Go back and look in your textbook on numerical methods for when Newton-Raphson fails. Yeah, okay. So actually this is dissolution. I clean it up. Come over here, put some clean up digits. Probably something like this. There you go. So here is my equilibrium composition, N. If I wanted to put it in terms of Y, we know how to do that, true? We just get the sum of the N's right here equal to sum. Notice that all of those, depended on Z. So it's going to be this divided by that. And because I want to copy that formula down, put a $sign so I'm not changing the location of the denominator. And go ahead and make those percent, give them one more digit, and then just check that they sum to, so they do sum to 100%. So those are the Y's. So you see that there's 4% CO in the products. And that temperature going out is lower than it would be if it would have been complete combustion, because the CO2 dissociates back into CO, which was our fuel. This problem is example problem 14.6 in your textbook verbatim.